So Joe gave the perfect definition of what a digital twin is. I'm going to try and bring it to life with some real-world examples and try and give a bit of context, a bit of flesh onto that bone of the sort of skeletal description. This is a rather flashy presentation. Those of you who saw my presentation last time, there's lots of photos of stuff I've actually done. This is one of our VPs was supposed to have given us a conference called ThingMonk in London last year. And at the very last minute, he bailed out and said, oh, I can't make it to London. He said, Andy, you're going to the conference. Can you give my presentation? Yeah, of course I can. What's this digital twin thing? But he said, well, here's my presentation. I'm sure you'll be fine. As it was, I was fine, but that means. So the upshot of that is I've got this very flashy presentation, so I'm going to capitalize on that as much as possible. And obviously, if you're a VP, you get the flashy moving animations as opposed to just the JPEGs that I get. So something to aspire to when we all become VPs, obviously. So the point of digital twin is really something which, as Joe said, but I'll say it again, it's a digital model of a physical system. And that can be anything from a city or a pump in a pumping station or a car or part of a human body. I was talking to some doctors recently who were doing some studies on part of the endocrine system. And they said, do we have to model the whole human in our digital twin, or can we just do a bit of it? And I said, I'm hoping you've just answered your own question in the way you asked that question, because no, of course you don't need to model the whole human. You just pick the bit you're interested in and model that. The problem is the bit you're interested in, because what you often find is that there are tendrils of data which actually influence the thing that you're looking at. And so you end up modeling more than you originally expected. But that's fine, because that means that you've thought about the problem correctly. And what we always encourage people to do is start from what we term the right-hand side, your right-hand side over here, which is start with what kind of question do you want to find the answer to? What are problem you're trying to solve? That will then inform what processing you need to do to what data in order to get those answers. So there's no point in building a digital twin or actually doing anything just for the sake of doing it, saying, here's some data, tell me something interesting. Well, that occasionally happens. It doesn't very often happen. You've always got to start off from the right-hand side with some kind of business outcome. And that sort of shatters the myth of AI. I was kind of hoping we could just throw the data at it and it could tell us all the answers. No, because if you do that, the answer's 42, right? So you're then going to go and find out what the question was. So digital twins go through the whole life cycle of a system. And when they're done properly and with most value, they incorporate the design, build, and operate phases of the life of an asset. So by linking that together in a sort of virtuous circle, by getting data from the operating system, you feed that back into the design process, so the next iteration becomes better in a sort of closed-loop system. And by getting early visibility of what's happening when your assets are in the real world, the things you make now, normally when you ship them out the door, it's the last you see of them. But now, by getting feedback from them, from IoT sensors and so on, you feed that back into the manufacturing process. So any systemic problems that have shown up in the manufacturing process and design flaws can be quickly identified and fixed. And in the operate phase, the ability to do predictive analytics and get insights into not only a particular running system, but also the whole class of running systems. So we're doing some stuff with Kona, people who make lifts and escalators. If you get in a lift, it either says Otis or Kona. Well, it might say ThyssenKrupp, but that's too long. You'll know which one it is. So the Kona ones, we're working with them to instrument all their lifts and escalators, and starting with the ones that weren't instrumented. So there's about 1.5 million of those around the world. And they feed back data, and what they do is they build digital twins of each type of escalator, each model, and they're getting data from all of them. So rather than monitoring just one of them, they're seeing all of them in their own little operating world. So that what they're seeing is a kind of a composite of one lift that's been subjected to every bit of abuse you could possibly throw at it, because somewhere in the world, one of those lifts will have experienced that. So the digital twin is really battered and worn because it's seen life as all the other lifts have on together. And so when they say, what if we only go and maintain these half as often? They can play that out on a digital twin and see what happens to the model. It's tempting to say ooh whenever these animations slide, isn't it? So analytics at every step. So we tend to think of analytics as being sort of really complicated machine learning, AI type stuff. But you've got to think, actually, even going back to simple statistics, max, min, average type stuff can tell you a huge amount about a system. So I tend to think of analytics as being a sliding scale. Everything from simple stats on the left to digital twin and mathematical modeling in the middle, through to machine learning on the near right-hand side, where the algorithms, it's not the algorithm says it, it's the data you feed it that determines the outcome. And we sort of conflate AI and machine learning. They're pretty much the same thing. My witty response when people say, what's the difference, is that AI is what you call it when you're looking for venture capital funding. Machine learning is what you say when you're looking for the software developers to actually develop the thing. It's the same thing, just coming at it from two different sides, the sexy name and the reality name. And then on the far right, you've got what we tend to think of real AI, which is sort of the more human-like interpretation, like visual interpretation, video analytics, audio analytics. One of the things we're doing with Kona is dangling a microphone down the lift shaft and quantifying what a normal lift sounds like. And then, you know, when you get in the lift sometime, and you just, and you go, I'm not sure we ought to be in this lift together. If I have to spend the next 8 hours with you lot, no, I don't think so. But that's what the microphone does. So it can characterize what a good lift sounds like, and then as soon as it deviates from that, the system doesn't know what's wrong with it. It just knows that something's abnormal, and it calls an engineer out to go and have a look at it. When that gets tracked down to, I don't know, a bearing running hot in the pulley at the top or something, then that waveform gets tagged with that name. So next time it sees that pattern, Watson goes, right, that's probably a pulley running hot on the gear assembly. Oh, that's really clever. How did it know that? Well, it didn't know that at all. It didn't learn that in the slightest. It just attached a label to a waveform. But that's how things appear to be intelligent. But the business value of that, of course, is that you can send the right part with the right engineer, with the right skills, the right training, the right safety certification to go and fix that problem, rather than having to go send a first trip to say, what's wrong here? So that's where you get value from AI systems. Open and federated data is really important. This whole thing about open data and not open data is a bit of a sort of thorny one, because people obviously attach business value to their own data, and that's perfectly reasonable. But quite often when you gather data that's valuable to you and is probably sort of business sensitive, you're also gathering other data which is probably valuable to the rest of society as well. So maybe you're gathering temperature data and, I don't know, power measurement in your transformers or something. Chris. So the temperature and humidity could perfectly well be made into a public data set and made visible to anybody who wants it for cool stuff, while you keep the confidential bit to yourself for your business purposes. So always keen to get access to external data sources. Weather is a really important data set. It's historical and now and in the future. So you've got historical, nowcasting, and forecasting. IBM owns the weather company, which is kind of surprising, because you know the Weather Channel. Well, the company behind that makes the data, generates the weather, or makes the data, weather data, is the weather company, which IBM owns. And the reason we bought them is because so many businesses rely on weather data to make their businesses either operate, run more effectively, deliver a better service, or whatever. So people are linking in live weather feeds into their applications. An industry context is so important. If you build a digital twin, if you get a data scientist and sit them down and say, right, build me a digital twin from this data, it'll just be a model of the data. It won't have any context for what the industry is. So we always sit down one of our data scientists who's an industry expert and say, okay, see that little spike there in the data? What does that mean? They go, well, that's when the rain comes down and the culvert fills up and the floodgates open, and so, right, okay, cool. And so you're learning what all the data is, and what often happens is you spend the first few days of an engagement sitting down just literally eyeballing the data. So don't just think you can get your data, throw it into a big black box and answers will pop out. You've got to do the hard work up front. You've got to get graphs of it drawn and correlations and compare one thing to another, just so your brain gets to imbibe the context, the nature of the data. Then you can start to think, okay, what are those right-hand side questions we want to ask in order to get the outcomes? Ooh. I'll do it for you, it's okay. So our digital twin technology is based on getting data from the real world. So we use the Watson IoT platform for that, using MQTT, the message protocol, which sends data in from the Internet of Things world, the physical systems, to feed the digital model. And then we get these cognitive insights or the analytical insights. And the key thing there is to make them into actionable insights. So there's no point in having a report a week late saying, oh, this, and this happened last week. What you really want to know is this, and this are happening at the moment. So you've got time to actually go and fix it. Or even better, do predictive analytics to say this, and this will happen in the next few hours or days. And that's really what we sort of term the low-hanging fruit for digital twin, particularly in the industrial IoT area, is predictive analytics. So being able to say that a robot on a production line is likely to fail in the next 24 hours is so valuable. Because if you have a production line with 10 robots on it, if one of those robots fails, it stops the whole production line. That can be thousands, tens of thousands, even millions of dollars a minute in lost production, depending on what you're making. Whereas if you can, in the maintenance window before the batch run starts, you can say, okay, do your normal preventative maintenance, and then here's a list of things that you wouldn't expect to have had to fix, but I'm telling you, you better fix, because I predict they're going to fail in the next few hours, and you do them during that maintenance window, you can then have a clear run of the production, and that's hugely valuable. And the key thing with a digital twin is that you have this dynamic recalibration, so you're keeping the digital model in sync with the physical world, not always just in strict real time, because sometimes, as I mentioned with the Kona example, you want your digital twin to be a kind of an average of all the ones that are out there, but you need to feed them with regular data to bring them up to date from the physical system. And it may be real time, it depends what you're modeling, but at some time interval, you want to be calibrating the model to make sure it doesn't drift too far away from reality. Because what we then tend to do with the digital twin is make a set of changes to the parameters and then run forward in time to see what will happen to the physical system in the digital world. And if your input state, as we've seen with weather forecasts, the butterflies wing in the Sahara can tornadoes in California, or whatever the metaphor is, but a small change in the input parameters can make a vast difference to the output as you move forward in time. And what we tend to do is run an ensemble of digital twins with slightly different input parameters. So you can see, say you change two parameters, you get a surface, you get a map, like a heat map of how the result comes out, and you can see how stable that is. So if it turns out the optimal value is balanced on a pinpoint, and it can fall down to be very suboptimal either side of it, that's not a good outcome. But if you're sitting on a nice, stable surface that you've got a fair bit of variability before anything starts to go bad, then you're in a good state, because you can get quite a lot of variation in the physical world before you have to go and do something to change the system. This is an example from our very lovely Highlight Towers building in Munich, which is the IBM Internet of Things headquarters. And we've done some digital twins of the 10 floors that we own. So one is dynamic recalibration of the heating system, which you might think is a frivolous exercise, but actually it's one of the hardest computational tasks known to man, because the heating system and cooling system definitely has a life of its own. And there are no people in the building who know how it works. So we've modeled its behavior using heat sensors under all the desks, and built a model over time, so we can then play what ifs. And what if we turn this thermostat down 2 degrees? What if we turn that one up 3 degrees? What's the overall change in the system? And we've built a model now so we can actually work out what we have to tell the BMS controller, i.e. the people who run the building, to do to the heating to make it so that it's pleasantly warm across the whole floor. I say, it sounds like a trivial pursuit, but in fact it's quite a major issue for our employees there, because they can't open the windows because they're like 20 floors up, and it's pretty dangerous. Another one is walking efficiency. So we have a robot down at the reception, those Pepper robots that greets you and makes eye contact with you and does a little dance and stuff, and then you can ask it where you want to go. And you say which floor number and which room number. And based on lots of journeys from lots of people between lots of rooms in the past, it tells you the optimal route to get to the room you want to do, which is really cute. Hey, when you got the elevator, and it takes you there. Of course, you don't remember the route when it's got to the third turn, but it doesn't really matter. The point is it has told you the optimal route to get to the place you're looking for. And that was based on, say, recording hundreds of journeys between different offices from employees moving between meetings. And the final one was environmental impact. And this is, those of you who came to my talk last time, remember the glow orb, this little device that's a single pixel output device that glows different colors. We've got those in all the meeting rooms on the table, and they are linked to the environmental monitors, which measure, amongst other things, the CO2 level. And you know when you're in a meeting and it kind of gets a bit, after the first couple of hours with 20 people sat around the table, it gets a bit stagnant and you go, oh God, when's this meeting going to end? Well, it's probably because the CO2 level is way up. And so what these little glow orbs do is they start pale green and they get increasingly red as the CO2 level goes up. And when they're red, it's not like the CO2 is dangerous, you're not going to die or anything, but it's probably a good indicator that your meeting is probably stagnated. It's probably a good time to have a leg stretch and go and get a cup of coffee and just kind of walk about a bit. And it's amazing how much of a sort of psychological icebreaker it is. Somebody goes, oh, look, glow orb's red, time for a coffee. And you leave all the windows open, doors open, and it's all nice and green when they come back again. And so it's an incredible productivity booster for long, tedious meetings. Probably the answer is not to have long, tedious meetings, but sometimes we do. And so this is analyzing the CO2 levels. And again, it's trying to make a model of trying to net out the difference between what the heating system's causing, sort of natural ventilation, and what the people in the room are causing. So we net off the number of people invited to the meeting for a number of time, which generates a model of what the CO2 should do in there. And in fact, one thing we've done is we can actually estimate how many people are in a meeting based on the rate of change of CO2 level, which is quite cool. So we can do things like bring the right number of cups of coffee, or right number of biscuits or something. Or just say, there's too many people in that room. Just have a smaller meeting next time, it'll be much more productive. Let's turn to 957. So this is an example of a company we work with very close called Schaeffler. They make the sort of the sub-assemblies for things like trains and trucks and things. So they've got the chassis and the carriages and the bogie assemblies. The gratuitous video here. This is an animation of a train, not even a video of a train. How much do we pay for these things? So VP's privilege, you see. So this is, it's an example of the kind of stuff that Schaeffler makes. And they are, as we move towards a model of, sort of what's termed servitization, which is a horrible word, but it's the idea that you don't buy something, you buy the service that that thing provides. So if rather than buying a washing machine, you bought from, I don't know, Bosch, or whatever, clean clothes as a service, then the thing you actually want from your washing machine is clean clothes. You don't actually care how it's delivered. It then becomes in Bosch's interest, or whichever company it is, Whirlpool or whoever, to keep that machine running for as long as possible, as efficiently as possible, and in fact, to preempt any breakdowns so that you keep getting your clean clothes rather than having to wait for weeks on end for an engineer to come, or indeed for planned obsolescence to make the thing break down after a few years, so you have to buy another one, because you never do buy another one. You're a bit like radio rentals. You remember radio rentals? You just have the thing as a service. So the famous example for this is Rolls-Royce power by the hour. So you don't buy a Rolls-Royce aero engine anymore, you lease power by the hour. And it's up to Rolls-Royce to make sure that your plane delivers that power for every hour that it's turned on. So then Rolls-Royce instrument their engines, they get live data coming back from the flight. If it's urgent, it radios it via the satellite link so that there's an engineer with the right part to fix it when it lands. When the plane lands, a ton of data gets offloaded, if that's the correct term for data, over the Wi-Fi, which then gets sent back. So you get several terabytes of data for each flight, which is then fed back into the big digital twin of that model of aero engine, so they can see how they're behaving in different situations. So the digital twin that Schaeffler have built is of these carriage assemblies, and they look for vibration in the wheels. So that tells them two things. One is that the wheel itself is damaged, or if they get a systemic problem at the same place on the track, they can tell there's track damage as well. So they actually feed that back to the rail network maintainers. But their main interest is in looking at sort of sounds coming from the engines that show that there's a fault. So the wheels show that there's a fault in it. Whoops, where did we go? Oh yeah. So the effect of that is that you've got full traceability. So remember the design, build, and operate thing. So that's across the whole life cycle of it. And being able to do predictive maintenance means that they can, obviously the average speed of a train is not how fast it goes on the track, but how long it has to stop for maintenance. and they can increase the average speed of a railway system by minimizing the maintenance schedule. And they can also look at sort of safety margins. Remember I talked about that error surface using an ensemble of digital twins? Well, they can see, well, if we ran it fractionally faster or fractionally slower, what's the window of safety that we can operate inside, and potentially operate the train at higher speed, because they know exactly what the effect of that higher speed is on the important bit, the bit that's keeping you stuck to the track. And the other big company we're working with on this is Airbus, where they're very much into digital twin right from the very, very early CAD/CAM design of the aircraft through manufacturing. And you've got so many sub-assemblies coming from subcontractors all the way up a supply chain. And it's really difficult to make sure everyone's talking the same terminology, and doing traceability of these air critical systems, flight critical systems, is really important. So they've got this digital twin. Somebody pointed out the tail seems to have fallen off this airplane. I'm not quite sure what's going on there, but I'm sure they'd notice. You don't need a digital twin to know the tail's fallen off your plane. But I think the point they're trying to make is that the digital twin is an ensemble of all the things that have happened to planes. So not just the one that you're on, but the ones that have gone before, well, even ones that have lost their tails and are still flying somehow. Because the stresses and strains on the aircraft are being fed back into that, and that goes right back into the build and design phases to say, wow, I can't imagine what would happen to this particularly beaten up aircraft, because it seems to have all these different things that have happened to it, because that's the ensemble of all the things that have happened to different ones. The biggest advantage for Airbus is really because they've got different disciplines and different vendors and this supply chain, is being able to have visibility of the same plane, the same model, so everybody can gather around it and see their bit of it and talk about it in the same terminology. So that digital twin, the main benefit is not actually in the twinning bit of it, or the physical input. It's the CAD/CAM build system all being integrated, and getting that consistency between viewpoints. And then understanding the impact of changes, because they've got this model of what this idealized or non-idealized plane is. They can see, what if we change this particular, make this bracket thinner or something. They can see what the stresses and strains, they can run it through the finite element analysis and look at what the impact of that is before it gets anywhere near a real plane. So they can do what pharmaceutical manufacturers are trying to do with their molecules, is try them out in the computer in silico before they get them into real use. So digital twin brings you better products, faster time to market, and new services and business models. So all those things flow very naturally once you've got your digital twin. We do time, excellent, right. So that's the really flashy digital twin talk from Chris. I just wanted to link that, sort of bring that to life with a couple of examples of what I've done with digital twin. Digital twin doesn't have to be big and complicated and modeling a whole aeroplane. You can start really simple. I just want to give you some examples of a couple of things I've done. One is that I built a digital twin of my home energy use. And that was, so essentially have a set of appliances in software that come on and go off at the right time. So the fridge comes on and goes off every now and again. The cooker comes on occasionally. The shower happens at certain times. The kettle comes on at regular intervals. And the energy that they generate is not actually using real energy. It's just generating the numbers that the energy monitor would have seen had those appliances been there. So I've got this thing called the e-house, which is online. And people live in it, so, well, not people, actor scripts live in it, and they act out, so like the family comes and goes, and they have dinner, and they get up, and they go to the toilet, and have showers, and stuff like that. And the overall effect, if you look at the trace of the e-house compared with my house, is very, very similar. You'd be quite hard pushed to look at it and go, nope, that's a computer model, and that's the real one. It's just been really interesting for me, so I can look at things like what's the effect of getting solar panels, or what's the effect of getting an electric vehicle on the overall usage, and if we start doing demand-side management, or if we start looking at variable tariffing, I can start to play some what-ifs with that and see what the effect would be on my lifestyle if I were to have those different things. And that's been very useful to inform the energy industry about whether these things would be useful or not. So another area I've been looking at is taking a twist beyond digital twin which is, so you've got a digital twin of a physical system, and then what I do is take some of the parameters from the digital twin and reimagine them in the physical world. Doesn't make sense. I call them physical digital twins, which is a really stupid name, but I can't think of a better name at the moment. So here's an example. So remember Highlight Towers, the Munich one? So we own, IBM owns 10 floors on this one and 1 floor over there. And it's just this lovely building. I was working in it for 6 months. I just fell in love with the building. And one day, just because I thought it would be really cool to build a 3D model of the building. So I got a clipboard and pasted around it and measured the size of the floors and counted the number of floors and stuff like that. And built a model of it in my computer, which is quite nice. And then printed it on my 3D printer, which is a 2-color 3D printer, I should add, one of the posh ones. So I did the inside bit in translucent plastic, as the floors that IBM owns. And then we put it on a laser-cut base. We actually make them as little trinkets for visiting dignitaries. So when they visit Highlight Towers, we give them one of these to go home. Now, what they don't realize, they might realize if they look, it's on the bottom is a QR code. If you scan the QR code, you get a page with a big red button. And the big red button, when you press it, turns the lights on. Yeah, that's so cool. And you click it again, they turn off. So you can basically control your digital twin. Now, the bit that makes it a physical digital twin is that further down this page, there's a little slidey button. And then you slide that, this actually changes to be the actual light level of the building. So when the lights are all on during the day, it looks like that. But in the evenings, it dims down and people go home and start turning the lights off. That dims down and becomes sort of you can actually, so from my desk in England, I can see sort of the day in the life of Highlight Towers over there in Munich as my colleagues 1 hour ahead go home and turn the lights off and stuff. It's pretty cool. Actually, one thing that came from that was we spotted there was a light kind of in the middle here that was on all night. And I said, "Oh, why is that light on all night?" And they said, "Oh, I don't know." And they looked at it, and one of the big conference room lights was just stuck on all the time, 24 hours a day. Everybody assumed it would turn off automatically, or someone would come and turn it off, but neither of those things was true. It was just on all the time. And it's only from spotting the digital twin that we noticed that, so we now save quite a lot of energy by turning those lights off. Oops. This is the very iconic Hursley House, a place where I work in the UK. To the right of that is some more traditional office buildings, but this is our executive briefing centre. It was originally a big sort of stately home, as you can tell. And again, obsessed with my desire for 3D models, I built a 3D model of that in my computer. That was far more work than doing Highlight Towers, I can tell you. Definitely a labour of love. In particular, the number of chimneys, I was just astounded by the number of chimneys. But anyway, so that's a 3D model, and it's hollow inside, and I've put lights inside it, multicolored LEDs, so I can now produce a heat map of the different rooms, and you can switch between different views. So this is occupancy, so it's showing green, but the estates manager has got one of these on his desk, and he can turn it to heat map view, and it actually shows blue through red via purple of what the temperature in the rooms is, so you can actually balance the heating system, which, as in Highlight Towers, is a non-trivial action, because these are all the ancient Victorian heating systems with radiators, which are a force unto themselves, so they can keep the environment pleasant for working in. So that's been really useful for that sort of, it's almost unintentional consequence, that white roof gives you that diffused heat map view across all the rooms, which is quite nice. So you see how we're taking a physical system, which has got sensors in all the rooms, making a digital model of it, and then reimagining that in the physical world in a very sort of tactile, meaningful way. The final one is a consequence of living on the Isle of Wight. Is that I go to work by ferry every day, and if you Google for stuff I've done, one thing I did is made the ferries tweet when they leave and arrive from the ferry ports, so there's kind of the twittering ferries, which is really useful as a commuter to know when the ferries are running. And if you want one for Jersey, more than happy to help build one. Anyway, so Red Funnel made a Lego alternative called Kobe model of the car ferry. My children bought me one for my birthday, which was great fun to build. Took a couple of hours, quite entertaining, and very pleasing that it was just like the Red Funnel ferry. But after that, I thought, well, that's a bit boring. It's just going to sit on my desk and gather dust now. So what can I do with it? How can I kind of pep it up a bit? And I thought about the data I was getting from the tracking system of the ferries, and also thought about boats. They have lights on them, like red on the left and green on the right and white on the back. and they have mast lights which show the direction of travel. I thought, oh, wouldn't it be cool if this had real, actual working lights? So I prototyped a system, as you do, with red and green and white. And because this is a ro-ro ferry, so it can go either way, so it just reverses direction, and they look out the other window and take it back the other way. So there's actually a red and a green on both sides, and they flip them round when they reverse direction. So that's what this was modeling. I had to build new masts, so I could put the LEDs in, so they made a little 3D model of the mast and put in a 3mm LED, which is quite nice. So in pairs, they can point that way or that way. And then built all those electronics into the model itself, and see how we've got the red and the green on both sides there. So now we've got a working lighting system. So we've got either red and green or green and red. We've got white on the back, and we've got these mast lights that light up. And okay, so that's quite pleasing. I could flip a switch and it would go from one to the other. But even better, because I'm getting live tracking data off the ferries, I can actually link this up as a physical digital twin of Red Osprey, so that when it's going along, it actually shows the direction of travel. So this sits on my table, and then if it's going south, it lights up with red on that side and green on this side and white on the back. If it's going north, this one lights up, and it goes red on that side and green on that side. And it shows the actual direction of travel of the boat. If it's parked, the correct thing is that you turn on all the white lights, so it turns off the green and red ones and turns on all the mast lights to show it's parked. So it comes in, parks for a while, and then the lights go off, and then it sets off in that direction. So I can actually see the running of it. Now, if you've ever been in the sea when the ferry's coming towards you, you'd see something like that. And that's coming through the mist towards you is actually pretty alarming. If I've been in a kayak that close to a ferry before, like, this is a bit scary. And it's very realistic. And when I come into my study at night, I think, the ferry's coming towards me. It really is a very sort of visceral interpretation of the thing of the ferry. So digital twins can be lots of fun, and hopefully that's given you a bit of insight, and I hope that's given a setup for the rest of the day. Thank you very much.